I guess I steered everybody into getting water.
Good. Tell me when I should start. Should I get started? Okay, so hi everyone. We did a brief presentation before. I'm Marco Velli, and I'll be walking around as I give this presentation today. So this is going to be an overview of solar, stellar winds, magnetic activity. It's kind of a historical and somewhat basic overview of some of the sort of basis of the physics and how we got to where we are. And then tomorrow we will continue in a little bit more quantitative way. So let's get started with, the sun, the solar corona, the solar wind. So one of the important things is that the sun is a star. It emits a lot of energy. It gives us essentially a kilowatt per square meter at the Earth. It's called the solar constant. And the corona and the magnetic field and CMEs and all space weather is driven by a very, very small fraction of that energy. It's a few thousandths of a percent in terms of complete energy. But it's very important because the release is not continuous, steady, and distributed uniformly in space as the solar radiation is. And so that's where the interesting problem starts. Now, the solar wind, the result of this magnetic activity, it creates a cavity in the stellar medium that extends about to 100 AU. As you all know, we've crossed the termination shock. And that's called the heliosphere, which is our basic playground, which we're talking about throughout this week, where the flux of cosmic rays is regulated by scattering. And of course, solar and stellar magnetic activity is really important for the possibility of having life elsewhere and habitability of planets and things like that. So this first part is going to be a kind of a geographical, historical tour. Then I'll talk briefly about solar and stellar activity and magnetized plasmas, and then some of the observational properties of the solar corona and solar wind from the first measurements, the Mariner spacecraft, and all the way up to Parker Solar Probe and Solar Orbiter. So, as you know, far out in the uncharted backwaters of the unfashionable spiral arm of the galaxy lies a disregarded yellow sun. That was Douglas Adams. And that's where we are, but we are very, G subdwarf. And the sun is sitting in an interstellar medium which is quite complex, where there's dust clouds, interactions of supernova remnants. And so the medium outside of the sun is quite complex. But of course, we're protected from all that because of the solar wind, essentially. And there is a termination shock, bow shock, that's not so clear. Probably not exactly, not the way we would have normally thought of it, but we'll get to that and the shape of the heliosphere towards the end of this talk. So just a reminder of the sun. So we sit at 215 solar radii, 150 million kilometers. That's one astronomical unit. The radius of the sun is about 700,000 kilometers, rotates in 25 days, 26 is seen from the Earth, and there's a differential rotation at the photosphere, where the poles rotating slower than the equator. And the magnetic activity is dated, what was discovered, or was observed, probably thousands of years ago. But it wasn't until the 16th century and the kind of invention of modern science, so to speak, that it became important. Now, historically, it's really interesting because, sunspots are attributed oftentimes to Galileo, but it wasn't really Galileo who discovered sunspots. But it's interesting because the dynamics of science has a lot to teach. So Galileo was a very important scientist. So like very many very famous, important scientists, he was not a very nice person. So in fact, the discovery, this is one of the sort of four basic discoveries. Galileo is credited with proving the Copernican system via the discovery of the Galilean satellites of Jupiter. And then he discovered the phases of Venus. And of course, sunspots is one of these important discoveries. And what actually happened was that a Jesuit had studied sunspots on the sun and wanted to talk about this, but he couldn't because, of course, the sun was supposed to be perfect, right? So he was a Jesuit, and so he couldn't go against the Pope. And so he anonymously wrote to a member of the academy that Galileo had founded, the Accademia delle Lincei, and said, you know, there's this really interesting stuff. And so this German merchant, Marcus Wessler, who was also an academician, didn't know much about this, so he sent these things to Galileo. And Galileo writes back to him and says, no, I know all about this already. I've discovered this stuff. And that's the first publication. And in fact, this is the drawings from Galileo himself. But then Scheiner managed to publish in the 1630s his observations. And really interesting things that you can see. He discovered that, for example, he showed that this solar rotation axis is inclined with respect to the orbit of the Earth by about 7 degrees. And so these were very important calculations. And by the way, his book, which of course has all the accessories, so to speak, of the times, you know, you had to show that you were respectful towards the noble people that were funding your research. Not very different from today, but in a different form. From today. And his book is available. You can find it online, actually. You can find the first edition costs about $145,000 if you want. Anyhow, so these are the important discoveries about sunspots. Let's fast forward quickly. Of course, we have the discovery, of course, the periodicity. Then Carrington associates sunspots with a white light flare. And then, of course, the famous Carrington event. Fitzgerald then starts thinking about how is it that when, you know, if a flare occurs and stuff happens at the Earth, what's going on? What's propagating? And at the end of the 19th century, there's a problem because Kelvin, or Thomson, who becomes Lord Kelvin, actually at the same moment where he becomes Lord Kelvin, tries to calculate if it's possible that the sun's magnetic field influences the Earth. Now he does a calculation which doesn't know that there's a solar wind, so he thinks only of the inductive effects of the magnetic field on the sun, and it's not possible. But of course that has a major role because it essentially paralyzes the study of the influence of the sun on the Earth in the United Kingdom for 30, 40 years. Okay, keep going. The Wolf, the sunspot number, the calculation, and now it's the Royal Observatory in Belgium that's responsible for carrying out detailed statistics of the number of sunspots. Sporer. There's a magnificent study of the sun using telescopes by Angelo Secchi. And then, of course, the study of the historical part, Maunder, and the sunspot and the butterfly diagram. And we now, have a very good statistic on solar cycle and the correlation between solar activity and time, and the fact that it's quasi-periodic. There has to be a dynamo. We don't know how the dynamo works, though, and so on. Fast forward to the 1920s, when George Ellery Hale, who's a really important figure in the history of astronomy and of heliophysics. Hale was a solar astronomer and invented the spectroheliograph. And he observed sunspots and immediately saw the Zeeman effect in sunspots, and therefore derived the fact that sunspots are magnetic. Hale was really important because he was also from a very wealthy family, and he funded the 100-inch telescope that discovered, for example, through which the expansion of the universe was discovered. And he also funded Mount Palomar, the 4-meter telescope, which was for many years the largest telescope. He also distributed his design for the spectroheliograph to other observatories in the world, in particular Florence and Arcetri, which also ran a solar tower with a spectroheliograph for many years. So today, we know a lot more about how this kind of works experimentally, so to speak. And this is an image that shows, from Hathaway, that shows how the monthly average of sunspots and magnetic fields is distributed on the sun. And what you can see here is Joy's law, sunspots that appear, that are inclined, and one polarity tends to propagate towards the equator, the other polarity tends to rush to the pole, and then the solar cycle then inverts. And so you can see that over the full cycle is about 22 years and repeats more or less quasi-periodically. That's the surface of the sun. During solar eclipses, you can get a glimpse of the fact that the sun does not end where it seems to end, but extends into space. And in the 40s, it was discovered that the gas here emits lines that were originally attributed to strange elements, coronium, because we didn't have experiments on the Earth that could produce the right lines. But Grotjan and Edlin in 1942 showed that these coronium lines were actually lines from multiply ionized iron. And that meant that the temperature of the solar corona had to be somewhere above 1,000,000 degrees Kelvin. The light that you see is mostly light scattered. The white light is from scattered light from electrons that are just redistributing the light from the photosphere. But if this is above 1,000,000 degrees, then we have a very strong ionization, and this gas is completely ionized. So why is there structure? That's question number one. Why is this? What can give structure to a medium like this? And of course, the only thing that can provide structure, the reason this is not a homogeneous ball, is magnetic fields. Now, as a consequence of that temperature, Chapman and Cowling derived that such a hot electron gas, that atmosphere should extend much further out than what we believe. And they thought that you would have a static atmosphere that extended all the way to the Earth, and therefore the Earth would be immersed in this gas of ionized particles. Now, observations of solar eclipses over many different years show that the shape of the corona changes dramatically. And so clearly the corona is the result of an interplay between an extremely hot ionized plasma and a complicated magnetic field, which is generated at the sun. And so we are already beginning to see that there is an interplay between the magnetic field generated inside the sun and what happens in the solar corona as a result of that. Now, this magnetic field plays two roles. It's kind of, you can imagine it, seeing it here. If you have a 2,000,000 degree gas, this magnetic field is containing the gas. It's providing the structures that you see in the corona. But on the other hand, it also has to be dragged open because this gas has to somehow expand outwards. Now, those are static images of the sun. We know that the sun is, as mentioned before, the sun is extremely dynamic, and the activity results in energetic phenomena that are of extremely high energies, solar flares, for example, where you have energy releases which are enormous over periods that are very short, tens of minutes, 20 minutes. And now as we learn more and more about that, the substructure of the corona and the dynamics of the corona plays a role. So the corona has to be heated, right? There's a thermodynamic problem. The photosphere is sitting at 6,000, 5,000 something degrees Kelvin, 5,600 degrees Kelvin. The solar corona, as the temperature is above 1,000,000 degrees, there is no way, no obvious way, in which thermodynamic processes can provide for the temperature to go up when the source of the energy is at the center of the sun. There may be ways, and we'll discuss them briefly, where non-equilibrium thermodynamics might help to do this. Now, coming back to stars, where do we see corona and chromospheres? Well, typically these things happen on because there's a kind of a separation line in the Hertzsprung-Russell diagram, and the activity is mostly confined to cooler stars where convection is readily occurring inside the star itself. Okay? So corona and chromospheres tend to die out when convection in the star tends to be missing or very limited in space. And that sort of shows that there's a relationship between the magnetic activity of a star and the dynamo processes that are occurring inside it. So another problem is, how are magnetic fields generated? So what's going on inside a star that produces the magnetic fields we see? Now, a bit of context about our sun and other stars. So here we have an image of the sun, and I like to show this because this is to scale, right? So this is the sun, this is Sirius, which is slightly higher temperature, 10,000 degrees. This is Sirius, and now we start moving towards the red, what are called red giants, Pollux, Antares, Aldebaran. That's Aldebaran. This is Betelgeuse, as you know, or Betelgeuse, as you say in the US. But as you know, this star is dynamic and expanding and contracting. And so you see that the scales over which these stars exist is very wide. And if you imagine now, this is the sun, again, as I said, this is Sirius, and you go to Antares, you see that this star then extends essentially beyond the orbit of the Earth. So you have stars where if the Earth were there in that system, we'd already be englobed. This is really important because as the sun will age, it will also go through a red giant phase, and this is what we expect to happen. So this is the current sun, and this is what we call the habitable zone, where you can have planets that can have atmospheres. And as the sun becomes larger, then the habitable zone is going to have to move. It's going to move away. The Earth might survive. It's not clear whether the sun will ever become large enough to actually englobe the Earth, but it's clear that the Earth will not be very habitable, so to speak, in a few billion years. These are now, this is the Hertzsprung-Russell diagram again, and we are seeing exoplanets. And you see that a lot of the exoplanets are actually seen around the reddish stars and convective stars. And in fact, just recently, I think just the other day, a paper is published in ABJ about a rocky planet with a helium atmosphere around a red dwarf. So these are some of the areas, promising areas, where people are looking for exoplanets which may have life, and where, of course, magnetic activity is fundamental. Okay, we talked about the corona is seen in a solar eclipse, but immersed in the corona, there is other stuff. There are solar prominences, and this is an example of a solar prominence. This is the size of the Earth. This is what's called a cloud prominence, and this is a prominence seen in the 171 line. Let's see if I can get this thing. Why isn't this running now? Oops, sorry. Let me click this so that you can see the movie, because it's important to have, I want to bring up the fact that prominences are not the idealized thing. This is a quiescent prominence. And you'll notice that this thing is huge, first of all. It's quasi-two-dimensional. It is extremely thin in one direction, extremely tall, and the length of a prominence itself can be over a solar radius. This is tens of thousands of kilometers high, 30, 40,000 kilometers, but the thickness is maybe 1,000 kilometers or so, a couple of thousands of kilometers. So when you look at this, you have to look at it without the prejudice of simple magnetic field configurations that we're used to. And I'll leave it at that for the moment. The magnetic field around a prominence is complex, and one of the discoveries of, thanks to the SDO and others, is that actually the corona displays some of the cellular structure that you see in the photosphere and in the chromosphere. And these are so-called coronal cells that align along the axis of a filament. So in fact, the magnetic field in the neighborhood of a prominence is heavily sheared. It is not a simple potential field, but has a very, very strong component of shear, meaning that there's free energy in the system. Okay. Yes. Oh, yeah, sure. If you guys want to, can interrupt me anytime, please. I'm happy to make, if you see something that you think contradicts something that you know, or if you have a question, yes.
Let's start with a simple question. What is shear component?
Okay, so we'll get to that later, but it's okay. So magnetic fields can be potential. They can be isolated from the currents that generated them from them, or they can be co-spatial with the currents that generate them. When the magnetic field is co-spatial with the currents that generate them, there's associated free energy. That's the simplest way I can say that.
I had another question about the diagram. So you were talking about how, I guess, that's how I remembered it, that coronas died out at sort of certain temperatures, I guess.
Yes?
So we actually see coronas of other stars, or this is just some theoretical estimations?
Do we see the corona of other stars?
Yeah.
We see emission lines, yes, from the corona of other stars, yes. And we see winds from other stars as well. But we can get to that later. Okay, so the corona, as I've told you, is an ionized gas at 1,000,000 degrees. And so the solar corona is a plasma. So what is a plasma? A plasma, for those of you, a lot of you know exactly what I'm talking about, but for those of you that don't know, a plasma is a collection of charged particles that interact with an electromagnetic field which is self-generated, okay? It is not a set of particles like in a circuit that are forced to follow a field that you impose, okay? So the dynamics is intrinsically nonlinear. Its nonlinearity comes from the fact that the fields in which the particles move is generated by those same particles, okay? Now, as a result, you have these collective effects that are important, and plasmas are everywhere in the universe. This is a classic diagram. We have temperature on this side in millions of degrees Kelvin, and this side in electron volts. And here we have densities, and here we have the solar corona. You see small, low density, high temperature, active galactic nuclei up here, white dwarfs, high density, high temperature, the sun's core. And we're trying to do nuclear fusion, of course, confined nuclear fusion on the Earth, and that's sitting somewhere there. Of course, we haven't, the reason we don't have nuclear fusion or magnetically confined nuclear fusion is precisely that. Okay, so that's not a simple problem. In fact, this is my 2-slide version of plasma physics. 3 slides, okay? So for those of you who have not studied plasmas before, I'll try to give you a description of why the dynamics of plasmas is complex. So first of all, in a neutral gas, when you have collisions, the frequency of collision increases when you increase the number of particles and when you increase the speed of the particles. The faster you try to get out of a cinema at the end of a movie theater, and the faster you go, the more people you're going to hit, and they're not going to be very happy. Okay, so fast particles end up slowing down. As a result, slower particles end up accelerating a little bit. And you can call this essentially equilibrium thermodynamics. You steal from the rich, you give to the poor, you end up with a Maxwellian distribution. Okay? In a plasma, collisions reduce the size because it's Coulomb collisions. So the cross-section goes like 1 over speed to the 4th power. That means that the collision frequency goes with 1 over v cubed. And that's like if you were in a movie theater and you start moving fast, the faster you go, the skinnier people look. And if you go fast enough, they become little infinitesimal things that you can just cross without any trouble. In other words, if you put a force in a plasma and you have some particles that are going faster, they're not going to feel collisions anymore. So they're just going to be able to accelerate freely. And as a result, the rich can get richer. And you have a runaway effect. Okay? So that's one very non-intuitive aspect of a plasma. And the other is, of course, that you have magnetic fields. So plasma is different because in a neutral gas, you don't really care about magnetic fields until they don't become too strong. You don't want to walk into tens of Teslas fields. That's not good for you. But for, fairly weak fields, everything's okay. But if you're a charged particle, you're forced to rotate around the field. And this is actually, I hope, done properly. So if you're a proton or a positive particle, you rotate according to the left-hand rule around the magnetic field. If you are the Lorentz force, if you are an electron, you rotate with the right hand. And of course, because of the mass of the electron is so much smaller, typically the Larmor radius, the radius of this gyration is much smaller for electrons than for protons. The other thing is, of course, as a result of what I just said, is that in an ordinary gas, you tend towards Maxwellian distribution. So if you look at the number of particles as a function of speed, see something like that. And if you look at the distribution in 2 or 3D, it's basically isotropic. Now, if you're in the plasma along the field, if you accelerate a little bit of particles, they don't collide anymore. And so since the field does nothing for motion along it, you can form very fast particle flows along the magnetic field. So you're going to develop tails along the magnetic field. But then you have processes that will tendentially end up heating the gas in the direction orthogonal to the field. The particles can't escape. They're orthogonal, they're tied to the field. So that's going to show up more as a temperature rather than as a flow. And as a result, from that circular thing that you see, you'll tend to form distribution functions that have this kind of bicycle seat shape, where you can have anisotropies. They will tend to prefer the perpendicular temperature or the width perpendicular to the magnetic field, along with beams along the field. And so, again, this is very non-intuitive. Once these beams become big enough, of course, then something's going to happen, because you're going to have too much energy in this distribution function. It's going to become unstable, and it's going to recreate new magnetic fields and new electric fields that are going to relax this distribution in a way which does not involve collisions directly. Okay, so just to recap, in the plasma, collisions decrease as the temperature goes up. Faster particles collide less and can accelerate more easily. Charged particles to lowest order must follow magnetic field lines. But as a result of that, if most of the field is actually generated by those particles, the field also has to follow the particles themselves. So the self-consistent magnetic field ends up providing structure and confinement. Electric and magnetic fields destabilize and accelerate. And as a result of this, the particles in the fields are inextricably intertwined. And I think it gives you an idea of what it must feel like to be a particle in a field if you try repeating those two words together 10 or 15 times quickly. It kind of makes you feel what it must be like to be in a magnetized plasma. Okay, so let's keep going with our history here. So plasmas were invented or discovered in the 20s. And in 1940s, Hans Alfvén, the only plasma physicist to get a Nobel Prize in the 70s, noted that a different kind of wave could exist. And it was interesting. He got a lot of grief because everybody knows, this goes back to some of the things we were discussing yesterday. Physicists know everything until you hit something that they don't. And before they give up what they know in favor of accepting something which they don't, it takes time. So physicists know that electromagnetic waves are fast and high frequency. So if somebody comes up and says, oh, there's this really low frequency wave in this medium, they say, no, you must have done something wrong. So that's what happened to poor Hans Alfvén. But he noted that in a magnetized plasma, a kind of combined electromagnetic hydrodynamic wave is produced, which so far as I know has as yet attracted no attention. But he did go and give seminars, and of course, very bright physicists on the opposite side of the spectrum say, wait a minute, this is a very interesting idea. And Enrico Fermi immediately used this idea that these Alfvén waves could exist in the medium to try to figure out how cosmic rays are accelerated. Now I encourage all of you, this is the original paper on the origin of cosmic radiation, to read this paper. this paper is 5-6 pages long, perfectly accessible. Enrico Fermi was one of the best writers that I know of in the physical sciences. His books are extremely clear, and his papers are as well. So in this paper, he describes the first order and second order Fermi mechanisms for the acceleration of cosmic rays. Let's keep going. In those same years, of course, mid-50s, the fusion bomb went off, as you know, in the United States, early 50s. The Soviets understood that the Americans had a fusion bomb by some theoretical calculation based on photographs. Sedov, a Russian physicist, understood that the Americans had exploded a hydrogen bomb in the atmosphere by looking at a sequence of photos of that explosion and deriving, using dimensional analysis, a law determining how fast this thing was expanding and deriving from that how much energy had to be involved in the release. And that was way above any fission bomb could produce, and so it had to be a hydrogen bomb. Anyhow, when fusion was discovered, immediately people started thinking about creating machines that could provide fusion energy, unlimited energy. And the statement goes that fusion is always 20 years away. It was 20 years away when I was at university. It's still 20 years away today. So it's one of the constants of nature, apparently. But in the 50s, all this kind of research was secret. But by the time we got to the mid-50s, Kurchatov went to give seminars in the UK and even in the US, and he described the tokamak, a toroidal plasma confinement device, and described the problems that they had with these experiments. The problem was you could drive a current in this thing, you could start heating it up, and at some point the current would become unstable, and the whole thing would blow up. And as a result of that, you'd get nuclear reactions, but the nuclear reactions would be between the wall and the plasma, and that would make the machine unusable and unworkable because it became radioactive, and so it was a real problem. And that involved an instability called the kink instability, the M=1 kink mode, and magnetic reconnection. And so this issue of reconnection came to the fore, okay? So what is magnetic reconnection? Magnetic reconnection is an instability that's associated with self-consistent currents in a magnetized plasma. And current sheets develop whenever magnetic fields in this self-consistent system get tortured enough so that they essentially the currents shrink. So from basic electromagnetism, you all know that parallel currents attract each other, right? Now, when you have wires, though, you have distinct wires and you have other forces involved, right? So it's not a problem. In a plasma, when these parallel currents attract each other, it's a very highly conductive system, so you can't really mess around with the magnetic flux so much. So as the current tries to kind of collapse as a result of the fact that if it's moving in one direction, it wants to shrink because of this self-consistent attractive force, it generates on its own a repulsive force. A current is induced on its own that will try to repel it. But the problem is that at some point, the scales of this system are such that one of the two wins over the other. And once a current starts collapsing and has decided it's going to collapse, there's nothing you can do to stop it. And that's what happens in a solar flare. That's what happens in the kink instability that you see there. The result of the kink mode, you have a reconnection instability going on there. It's what happens in the magnetotail of the Earth, and so on. Okay, so that's why reconnection is so universally invoked and so often hardly understood, because it depends on the details of your system. Okay, we'll talk more about that tomorrow. But these are just examples of current sheets that occur and in which this universal process of magnetic reconnection happens. So for example, this is like the surface of the sun, and you can imagine some force creating some flux tube being extended, and you form a current sheet over here. The tail of the Earth, in which the solar wind is pushing these magnetic fields, and you have anti-parallel fields with a strong current, a neutron star magnetosphere, and so on. As a result of these collapses of these currents, you form islands and things like that that we'll get into better in tomorrow's lecture. Okay, so we're getting to the end of the 40s, and we've seen that there's a corona. There's an argument as to how far the corona extends out into space, and we've had rockets that have been going up. And this is a pedagogical book from 1948, an Italian book, and it's really nice because it shows you the state of the art in that year. You see the V2 rockets were going up, and you see the temperature, and you see the various layers of the atmosphere of the Earth, including the ionosphere, and you see the temperature here, plus 21 at the surface. You go up, the temperature goes down. You all know that when you're up 10,000, 20,000 meters, temperature goes down to minus 40, which is when Fahrenheit and centigrade are the same, so we don't have to clarify what that is. And then the temperature starts going up, and you see it says plus 100 question mark, and that's where Aurora is kind of sitting, and then there's another question mark here. And then he says, well, you should be going to minus 273, right? Because if that's a void, it's absolute zero, it's black. That's what I expect. But then in the early 50s, a number of people looking at comets realized that there are two different comet tails, typically. One which is essentially the orbital, due to the dust that's coming off the comet, it kind of follows the orbit. And then there's this other tail, which tend to be basically oriented anti-sunward. There's some small angular distribution, but it's mostly anti-sunward. But you can calculate, using this kind of distribution of angles and the speed of the comet, you can calculate what medium could be doing that, and you can get a speed for that. And so Biermann estimated that there had to be some solar corpuscular radiation, some particles moving away from the sun, and he estimated the speed to be about 500 kilometers per second. And Biermann is really interesting because Biermann was German, and Biermann was also working on the dynamo. You know that you've heard of the Biermann battery. Have any of you heard of what's called the Biermann battery? The Biermann battery is a system by which you can generate magnetic fields that are not there to start with. And it occurs when the gradients in density and temperature in an ionized medium are not parallel to each other. Then you have a source term that can generate magnetic fields out of nothing. That's called the Biermann battery. And he went to Chicago, where Simpson was, and a young postdoc, or early researcher, his name was Parker, who was also working on the dynamo. And he tried to tell people that, there has to be a solar wind. Well, the story is interrupted by the fact that the Soviets in 1957 launched Sputnik. So that's the beginning of the space age. And again, the beginning of the space age is interesting because it was something that everybody wanted, but were not sure could actually happen. So the Soviets had a group of Ukrainian, in fact, Korolev was a Ukrainian, trying to launch, but they weren't really, they were working on their own and doing this thing on this sort of on the side in some sense. So when Korolev launches Sputnik and it actually goes into space, the Soviets don't really care that much. The problem is that the Americans see the radio signal and they get really scared. And they get so scared that the New York Times has to write an article in which he tells the American public, oh, don't worry, this isn't scary. Because you can't use this to spy or to drop bombs. It's only interesting to study solar physics. That's what they say. This is Saturday, October 5th. Military experts said that satellites would have no military application in the foreseeable future. The satellites could not be used to drop atomic or hydrogen bombs or anything else on the Earth, the scientists said. The real significance is that it will tell us information about the nature of the sun, cosmic radiation, solar radio interference, and static producing phenomena, so on and so forth. And all this will be really important if we're working on the problem of sending missiles and eventually men into the vast reaches of the solar system. So we have a program now for solar research. Of course, that's not the real reason. So the day after Of course, the Soviets realize they've done something really important, and so then finally Pravda publishes. So that's an interesting point there. And at the same time, Gene Parker sends his famous paper on the dynamics of the interplanetary gas and magnetic field, predicting the solar wind. And that's a photo of me with Gene Parker at the launch of Solar Probe, and that's with a couple of students of mine and Gene Parker at a solar orbiter meeting a few years before that. In his older age, Gene had mellowed out, and we had lots of really interesting conversations on the heating of the corona and the acceleration of the solar wind, but I'll talk more about that tomorrow. Anyway, the gist of that paper is basically hydrostatics of a hot corona. All right, so this is the few equations that I'm going to show you in this hour and a half, more or less, okay? So remember, the acceleration at the surface of the sun, gm over rs squared, okay? That's related to the escape speed from the sun. The escape speed from the sun is, somebody tell me, what's the escape speed from the surface of the sun? Go ahead. No, 600 kilometers per second. Factor of 3. It's okay, you're same ballpark, but it's factor of 3. It's about 600 kilometers per second. Okay, so suppose then that you have a hydrostatic atmosphere. Then just dphi by dr has to be minus rho g over r squared, and there's temperature, and you get this integral here, and you see that you have t times r squared in the denominator. Now that means that if t falls down more slowly than 1 over r, see, if t is exactly 1 over r, then this is 1 over r. And 1 over r diverges both in r equals 0 and r infinity. That gives you both divergences. If it's less than 1, then it diverges on the left but not on the right. If it's more than 1, it doesn't diverge on the right but on the left. But on the left, you don't go to 0. You're at the surface of the sun, so it's okay. You're worried about what happens at r tending to infinity. And the point is that if T of r falls slower than 1 over r, a finite pressure at infinity is required to confine the atmosphere. Now, in a fully ionized plasma, I just told you that the collisions go down with velocity. The mean free path, or the collision frequency, n sigma v, goes down like v to the minus 3. Okay, that's t to the minus 3 halves. To find out the conductivity, you have to take t and divide it by that. And so that gives you a conductivity that goes like t to the 5 halves. So as you get hotter, the conduction becomes faster and faster and faster. And that makes things almost isothermal, right? Because if you can conduct heat really easily, the whole corona is going to be at the same temperature. But if you're isothermal, then T doesn't decay at all, so that's slower than 1 over R. But even if you do the calculation with T to the 5 halves, you get T of R going like R to the minus 2 over 7, which is less than 1. So that means that this corona needs somebody on the outside to push on it. Otherwise, it's not going to sit there. And so that's what he says. Since we know of no general pressure at infinity which could balance the P infinite computed from that equation, we conclude that probably it's not possible for solar corona, or indeed perhaps the atmosphere of any star, to be in complete hydrostatic equilibrium out to large distances. Now note that this evaporation is different from what we call Jeans evaporation. What is the Jeans evaporation? Jeans evaporation is the fact that if you have a Maxwellian in an atmosphere, say on a planet, there's always going to be a tail of the distribution where particles are faster than the escape speed. So you're going to have this slow dribbling away of the atmosphere. You always have that. But it's exponentially slow in time if you go and calculate that. Here, this is a hydrodynamic thing. You have to expand outwards. So Parker writes this trivially simple equation, which is the same equation that governs the flow of a gas in a nozzle. Okay? So you get something like Mach, or U minus the thermal speed divided by U du by dr. And on the right-hand side, you have that same thermal speed times this cross-section, 1 over A dA by dr, minus gravity. Okay? And as you can see, this equation has what's called a regular singular point where U is equal to the thermal speed. And du by dr, if the right-hand side doesn't vanish, when the left-hand side vanishes, is going to be infinite. And so you're going to be in trouble. And so Parker quickly said, well, wait a minute. The only way I can find a solution here is that when this guy vanishes, this guy also has to vanish, so it's a regular singular point, so I can smoothly go through this singular point and come out. There's only one solution here. This is the phase diagram of that equation, quite simple. You have this singular point where the right-hand side and the left-hand side vanish at the same time. And there's only one solution that takes me to small velocity at the coronal base. It's at zero pressure at infinity. And that's this thing. And that's called sort of the Parker solution, okay, of the solar wind. And people have struggled for many years. How does the wind know that it's going to have to pick that specific solution? And sometimes, even today, you see papers that ask that question. The question is solved. It's very simple. It's because this is a stationary equation. You've assumed the system is stationary. If you include the fact that there's a time derivative, it's actually a causal thing, right? Things have to talk to each other. In order to generate any kind of wind or motion, you have to have sound waves that propagate in your system. If you put the term d by dt on the left-hand side of that equation, there's no singularity at all. So it turns out that this Parker solution actually is an attractor of this dynamical system. It naturally goes there. So this singularity thing is kind of a fake problem, okay? All right, but at the same time, as Parker, as luck would have it, before people started analyzing that system of equations too much, Sputnik had been launched and NASA was formed as a result. Because in the US, the Navy, the Air Force, the Army, these guys were all fighting to do their own independent rockets, and it wasn't working. You know, the Vanguards were not flying properly. And so NASA is born with the Space Act, and Simpson from Chicago forms a committee and says, what are we going to do with these satellites once we manage to produce them? Well, we're going to explore the solar system. And one of the things we want to do is go close to the sun and see what on earth's going on with all this cosmic radiation coming from the sun, all this radio interference, this magnetic activity. We're going to try to study that. And that's 58. And in 2018, Solar Probe was launched. So it took a while, about 60 years. But in the meantime, the Russians continued, and Luna 1, also known as the Dream or Mechta, was launched to try to hit the moon. And on the way, they put plasma detectors and magnetic field detectors because they also wanted to see. The Americans sent the Explorer 1 in 1959 and 1958 and 1959, no, 58. And they wanted to measure the radiation belts. So but they also wanted to crash on the moon. It's not easy with a 1950s, 60s computer to hit the moon. So they missed. And so, missing the moon, they created the first interplanetary spacecraft, and they had measurements of plasma. And they kind of saw, they couldn't claim that it was continuous because they didn't have enough continuous measurements, but they saw streams of high-speed plasma. That's Gringotts et al. So they made the first measurements of what became the solar wind. And then, from 62 to 73, the NASA Jet Propulsion Lab was tasked with launching a whole series of spacecraft called the Mariner spacecraft. And Mariner 1 was launched on launch. This happened fairly frequently. But Mariner 2, that was going to Venus, actually went there. And this is a maquette of Mariner 2 being presented by Pickering, who was the director of JPL at the time. And the person that you see here, does anybody know who that is? It's a name you all know. That's James Webb. He was the NASA administrator at the time. You all know about the James Webb telescope, right? Well, that's him. Okay, so this is being presented to John F. Kennedy in 1963. Okay, so Mariner 2 made the first continuous measurements of the solar wind flow. And this is the NASA press conferences, which says, yes, we have measured the Parker solar wind. It's there. And if you look at, these are the data are public. This is a plot I made with the data from Mariner. And you can see that the measurements between 0.77, which is Venus, and 1 AU, which is the Earth, you can see the flow speed is varying. Now, a posteriori science is easy, right? We know that there are high-speed and low-speed streams. So I look at this, I say, I can see high-speed and low-speed streams right away. But of course, at the time, they couldn't say that, right? And so that's Marcia Neugebauer at the press conference, and Ed Smith, who passed away just a few years ago now, who's on the mission as well. And Marcia's still she's still doing okay. She actually came, saw Solar Probe in the works. And from the Mariner 2 data, so the whole series of Mariner spacecraft I was telling you about, quite a few of them worked well. Mariner 5 also went to Venus. And so here we have, in 1968, still using the Mariner data. Mariner 2 only had magnetic field data, but you see one of the first example. Not only is the solar wind there, but it's turbulent. If I look at the spectrum of the magnetic field, I see it's a power law. And so that's Coleman, 1968. And by the way, these are the years in which the theory of magnetohydrodynamics turbulence is being developed. Kraichnen and Yeroshnikov in the Soviet Union developed a modification of the hydrodynamic theory of turbulence proposed by Kolmogorov to the presence of magnetic fields. It's happening at the same time. And with Mariner 5, Belcher and Davis, Marcia Neugebauer with another researcher at JPL had seen, using Mariner 5, some instances of what are Alfvén waves. But in 1971, Belcher and Davis write this paper, and they look at the correlation between the velocity. Now, Mariner 5 has velocity measurements. It measures the plasma. And this is BR, VR, BT, RTN are the coordinates of the ecliptic. So what happens is that T is so R is the radial coordinate. T is the coordinate moving along with the Earth. So anti-clockwise, the right-hand rule. And N is R cross T. Okay, so it's from the ecliptic. And so here we have BR and VR, BT and VT, BN and VN, and this is mod B in the density. And what Belcher and Davis see in this data is that more than 50% of the time, yes, there are spectra, but this correlation, incredible correlation if you think of it, between B and V is Alfvén waves. So that thing that Alfvén had proposed in 1942 actually exists, and it's dominant in the spacecraft data in the solar wind. Now, this is not the simple Alfvén wave that Alfvén had thought. It's a more complicated animal, and we'll discuss it tomorrow. Why is it more complicated? You see it's all three components, BR, BT, and BN, are correlated with VR, VT, and VN. And the magnitude of the field is not oscillating. There are huge oscillations in the components, but the magnitude of the field is almost constant. So that means if you think of the magnetic field as a vector, the vector is moving all over the place, but the tip of the vector is following a sphere. So this is what became known as the spherically polarized Alfvén wave. And tomorrow we'll discuss it more in detail. Okay, let's come back to coronal heating now. This is an eclipse image from Shadia Habal, and it's showing the temperature as measured by using two different iron lines. And it shows that the corona is not sort of isothermal, but it has hotter regions and cooler regions. And you can see that the poles are cooler, and sort of the regions with closed arches, which we believe are closed magnetic fields, of course, seem to be hotter. And the other interesting bit is that the regions of the corona surrounding prominences, which are cold chromospheric material sitting up in the corona, are actually the hottest areas of the corona itself. And so that leads to the problem of coronal heating. So let's just quickly take a look. This is a beautiful picture that Steve Kramer put together of the temperature profile as a function of height above the photosphere in log. Okay, so that's why it's kind of... So you see the temperature has a temperature minimum, 2,000 degrees. Then it slowly goes up in the chromosphere. In static models of the chromosphere extends about 2,000 kilometers. So if you remember the sun is 700,000 kilometers. 2,000 kilometers, basically nothing. It's a very small layer. It's called the chromosphere because it looks red in eclipses, so it's got color. That's why you can see it. The real chromosphere, by the way, is not 2,000 kilometers. It's full of these things called spicules that extend up 5,000 kilometers. So already there's a basic physics problem, right? Because the theoretical quasi-static atmosphere has these things really narrow, but the real thing is alive and it's moving all the time and it's extended more than twice what you think it should be. And then over 100 kilometers, so help me, 700,000, 100 over 700,000, it's 1 over 7,000, it's less than 1 per, it's almost 10 to the minus 4. The temperature transitions from, temperature transitions to 10 to the 6. And that's called the transition region. And then we have, of course, this very hot gas. It very quickly becomes low density. And so as you can imagine, you'd imagine the distribution functions. And look, you see what I was telling you about distribution functions in a plasma? You see this is a bicycle shape. It's a classic example. Electrons and ions look a little bit different. Now, there's a region of temperature maximum, and thermal conduction typically would go away from the maximum in the temperature, right? So who produces all this thing? Well, there were attempts to do it with hydrodynamics. We have convection, we have turbulence. The problem is that sound waves that can propagate in a medium like this have a real problem. Why do sound waves have a problem? Because the density is going down as you move up. And sound waves already on their own tend to steepen and to form shocks. So if you calculate how high a sound wave can reach before it becomes a shock, you get something like 1,000, 2,000 kilometers. That means that they deposit all their energy in the chromosphere, which is very heavy. There's no way you can produce a corona. In order to produce a corona, you have to go higher up, deposit the energy above the transition region. Okay. And the only guy that can do that is the magnetic field. He's the only mechanic who can take energy from the convection below, propagate it upward, and dissipate it there. And so what is that? That's a Poynting flux. It's written down here, S dot n. So if you consider n to be the normal to the photosphere, there is a Poynting flux. Poynting flux is, hope your EM is okay, it's E cross B. And E, in a plasma, we didn't discuss this, we'll discuss it tomorrow. In an ideal plasma, it's essentially V cross B. So in other words, the electric field is short-circuited in the plasma. The electrons are so fast that you cannot make a potential difference in the plasma. And so that means that the electric field that I measure in the laboratory is equal to minus V cross B, so that the self-consistent electric field seen by the plasma is 0. That translates into two pieces. One is the upwelling of magnetic field from the photosphere into the chromosphere and into the corona, but that field has to be parallel to the surface because it has to be lifted up. It's called emerging flux, that first piece there. And the second bit is a magnetic field which comes up through the photosphere and into the corona, but then the turbulence moves it around. Now, depending on how fast it moves it around, that's going to go up as a wave. If the time scale over which this oscillates is short compared to the time that it takes things to go up, then it's going to look like a wave. But if this field's coming out and coming back into the photosphere, and this is really slow, then it's going to look like a quasi-static kind of motion. And this was Parker's intuition, which Amitava alluded to yesterday. Let me do this. And so so this is my magnetic field line. You can all see it. Now, if you imagine that this side is anchored in the photosphere, and for simplicity, we're going to turn off motion in the photosphere on this side. And this side's coming back into the photosphere. What's going to happen? If this is slow, this is going to kind of move. And as a result, you can see that the field line, which is originally straight, if you can imagine that, now becomes longer. For the field line to become longer, it means that I've introduced a magnetic field in this direction. It's like a dynamo. It's like a coronal dynamo. And what Parker suggested was, okay, if I've got this random motions and I've got this magnetic field, and the motions are slow because the density is so low, numbers. Sorry, got to backtrack. Sunspot. Somebody tell me, what's the magnetic field in a sunspot? Anybody know? Sorry? That's a good estimate, 1,000 Gauss. So if I put a corona at a density, say, I'm going to be heavy-handed here. I'm going to take density of 10 to the 9 per cubic centimeter. 1,000 Gauss is a lot because when you get to the corona, the magnetic field expands. Okay, so let's say that we're in a region which is above a sunspot, but not sitting right in the sunspot. It's probably going to get up being about 100 Gauss or something. So if I take about 100 Gauss and 10 to the 9, what do I get for my alpha and speed, the speed of propagation of these magnetic waves? Well, you can go and calculate it. Tomorrow we'll put the formula together. It's about 2,000 kilometers per second. Okay? So you can have a loop here. Let's say that it's 20,000 kilometers long. That means it's going to take 10 seconds for a wave to go back and forth. But the motion, photospheric motion, granulation, is slow. It's like minutes and hours. So this is really slow. So there's this coronal dynamo. And what did Parker say? Parker said, well, waves cannot readily propagate. If you're trying to propagate waves from a system where the speed is low to where the speed is high, you're going to get a lot of reflection. And so I said these wave motions aren't going to make it into the corona, but these slow motions will, because they're going to basically drag the field around. And then he said, but if I do dragging of arbitrary fields, and the corona is a conductor, a perfect conductor, I'm going to drive currents in the corona. And these currents are going to want to collapse. And he proposed his magnetostatic theorem. He said, if you put an arbitrary deformation of the magnetic field in the photosphere, I bet, or I suggest, I conjecture that the current configuration in the corona is not going to be smooth. Why do I need it not to be smooth? It comes back to the properties of the plasma I was talking about before. Remember the collision frequency. If the temperature is high, the collision frequency is low. That means that the resistance is very low. If the resistance is very low, I'm not going to dissipate a current, unless the current is structured on such a small scale that the resistance can play a role. And so Parker conjectured that you would have these currents, very localized current sheets that form in the corona. And once a current becomes small enough, remember I just mentioned, we have empirical evidence that they tend to collapse. And that collapse leads to these local flares he called nanoflares. He was estimating how much energy was required to heat the corona, and then he estimated these elementary events would be 10 to the minus 9 times the 10 to the 23 ergs that we were talking about before, and he called those nanoflares. And that conjecture seems to be holding up. Now, whether it's been proven or not is a different question, but empirically, I think we have a lot of evidence that something like that is going on. Okay, so sorry, let's keep going. So this is now this is an UV image from Solar Orbiter. Solar Orbiter is the first spacecraft that actually moves a large telescope in distance from Earth orbit. And you can see that the corona is dynamic. So this idea that you have this average corona it's going to work. I mean, you can always average, right? It's fine. But the dynamics is extreme. And I would like to point out this is a Proba 2 instrument that had a very wide field of view. You notice some really interesting properties. If you imagine that the magnetic field is traced by the plasma, you see that the expansion of the field into the corona is everything but homogeneous. You have very small regions of photosphere that end up occupying huge volumes of the solar corona. That mapping is non-trivial. That's a fundamental aspect of how the heliosphere works. It's associated with a whole series of issues that we still need to grasp with. But it's really important to understand that if you say, okay, we see the whole solar wind occupies 4 pi, but where does it come from? It doesn't come from 4 pi on the sun. In fact, it may come from very narrow regions on the sun. Okay. So the corona looks different for the solar cycle. This is a proof that stellar activity is driven by magnetic field. It's an empirical proof. It shows you that the magnetic flux correlates with the X-ray flux. This is from a paper by Pessoff. The correlation is extremely good. The sun is, all the different stars are on here, and you can see that correlation very well. And this is now an image of the detail of the chromosphere to corona transition, just to give you the difficulty of the problem at hand. Okay, so this is the photosphere. In the photosphere, you have convection occurring on different scales with peaks at what's called granulation and supergranulation, but there's scales intermediate in between. This is a unipolar region. then this is the chromosphere, where we have jets called spicules, and then we have this transition region here, and up here we have the corona. And this is an extremely inhomogeneous and turbulent region of space. And we have entire space missions devoted to try and understanding it, originally TRACE, now MUSE, soon to come, IRIS, etc. But really, we're a little bit, I think, in the physics of this, because it's so difficult, because it involves ions and neutral interactions and molecules dissociating and atoms dissociating and non-equilibrium thermodynamics is still, I think, we're a little bit behind in understanding how that works. Okay, now, forget all about that and let's take a simple dipole corona. And we have this 2 million degrees, so it drags the field out. So what happens? The result, it drags the field out. So these closed loops have to be dragged open. And now you see that the coronal heating, which is probably magnetic, now takes a part of that energy and stores it again in this macroscopic current sheet. Because that's a source of free energy, because the magnetic field has to go one way here and the other way here, which means you have anti-parallel fields, so there has to be a current circulating around the sun. That has energy in it, but it's a byproduct of the heating that brings the expansion. So the magnetic field originally heats up, and then takes some of that energy back and stores it in currents in the extended solar corona. How does that happen? Is that like a semi-continuous stationary process? Turns out it's not at all, and now we finally understood that. Then the sun rotates, and this is a highly conducting medium, so that poor magnetic field gets wrapped around in a spiral. It'd be nice if it were laminar, but it's, as we saw, we already have measurements that it's turbulent. Okay? The axis is inclined, so in addition to be spiral and turbulent, it's also warped, and so the current sheet itself, far enough away, develops a structure. It used to be called the ballerina skirt. I don't know how you want to call it. Let's call it the warped geospheric current sheet. In the early 90s, after a long delay, Ulysses was launched. It's the only orbiter to have gone over the poles of the sun. It's a spacecraft that went all the way out to Jupiter, got kicked out of the ecliptic plane, slowed down in ecliptic motion so that it would go over the poles of the sun. Actually went south first, then came out north, came down. And that gave us these are polar plots of the solar wind speed during different phases of the solar activity cycle. So it did essentially almost half a cycle, almost 11 years, okay? So first orbit, you see the solar wind speed oscillating, and that's because of this presence of this warped current sheet. So the wind is slower where the magnetic field has to be dragged open. And if you're sitting in the ecliptic plane, you cross this once, then you cross it again, and you have higher speed, lower speed, higher speed, lower speed, higher speed. And that's actually on this side. And then you go, once you get up to about 25, 30 degrees, all of a sudden, poof, you're in fast wind at solar minimum. And that fast wind has a speed of about 730 kilometers per second, okay? But it has an oscillation on it. There's a turbulence, even in the radial flow, of about 50 kilometers per second. So it goes from 730 to about 800, up and down, up and down, up and down. And there's a typical period of that thing of about a day or so. Those are called microstreams. And you come around, and now you're at perihelion. So aphelion was at 5 astronomical units, Jupiter. Then you come around, and now at perihelion, you're at 1.3 astronomical units, almost at the Earth. So you're going much faster. So you cross really fast, and so you see very few of these oscillations, because it takes a much shorter time to go from minus 23 to plus 23. And then you're out again, and again, you see these high-speed wind. So pretty simple. High-speed wind from the polar coronal holes, and this low-speed, complicated mess occurring where the magnetic field tends to close, where sunspots are, and so on and so forth. Solar maximum, look at that and you say, what's this gonna, yeah, it's a mess, right? Are we gonna build a theory for that? Let's try building a theory for this first. Then maybe we'll try addressing that, okay? And then the next solar minimum, which was the very deep solar minimum of 2009, interestingly enough, the field became very weak. Sunspots disappeared for, there were already incredible predictions in newspapers appearing, articles saying that we're going to face a new ice age because there is a very well-known correlation, historical, between magnetic activity on the sun and climate on the Earth. And so some people had the audacity to say that since human effects are not important, the fact that we had zero activity was going to lead to an ice age. Those years at the time were the hottest temperatures ever measured. Now, of course, we're well beyond, but those were, at the time, their peaks for that time. So there was no ice age because the correlation between solar activity and climate is gone. But the wind speed was the same. Even though there was no visible sunspot activity, the wind speed was still somewhere between 730 and 800 kilometers per second. That means that even though we were missing these huge fat sunspots, the local small-scale activity led to a wind which had a similar speed. The momentum was smaller. The density tended to be inferior, okay? But the wind speed was pretty much the same. And then they turned pyrolysis off. Instruments started failing. Long story, it was the last, I think it's the last, or next to last civilian spacecraft that had RTGs, isotope-heated electricity. And so it was launched on a shuttle, and there were protests because if the shuttle had something wrong with it, you had these nuclear things, people were afraid. And so, NASA kind of abandoned the idea of using RTGs. Okay, so this is to summarize fast and slow. So given the corona, do we understand the solar wind? Well, not quite. The fast wind is too fast. The temperature of the coronal hole is actually the coldest temperature on the sun. It's 1,000,000 degrees, but if you follow Parker, that would lead to a wind speed about 300 kilometers per second, not 700. So there's a speed problem. And then if you look at the correlation between temperature and speed, it's opposite. So there's one thing you can measure in the solar wind in situ, which Ulysses measured, which is the ratio of different ionization states of atoms. Now, where is that set? That ratio of ionization states, it's set at the last time the density was high enough for collisions with electrons to produce something. So it's a measure of the temperature of electrons where the last collision happened. So it's what's called the freezing in temperature. It's kind of a proxy for the electron temperature in the corona that sets that ratio. So this is the ratio magnesium to oxygen, oxygen 7 to oxygen 6, and that's the equivalent temperature. And it's showing you that the slowest solar wind has the hottest temperature, and the fastest solar wind has the coldest temperature, set at around 1,000,000 degrees. And the SOHO spacecraft, remote sensing, using a technique called the Doppler dimming, showed that the electron temperature, well, the neutral hydrogen temperature in the coronal hole was maybe around 2 million. Minor ions were heated much higher, to hundreds of millions of degrees. And so the coronal hole had this strange non-thermodynamic behavior. Cold electrons, hot ions. And then the wind speed is fast. On the other hand, the slow wind, much more thermodynamic. It's as though somebody had set off a bomb in the corona and let things go. Okay. And we had additional ways to measure that with interplanetary scintillation, and these are estimates of the profile of fast solar wind from interplanetary scintillation, which led to the idea that the acceleration had to occur very, very quickly close to the sun. And here we have an example from Helios spacecraft that was launched in the 70s, German mission. It went all the way to the orbit of Mercury, and we see examples of the distribution function as a function of wind speed. And so you see the highest wind speed, this is the direction of the magnetic field, typically has these bicycle-shaped distribution functions. So it's hot with a perp over parallel anisotropy, okay? All right. So these are details now. I don't have time to go into it, but this is the detail of the structure of the speed. See, this is 750 kilometers per second. This is the radial velocity. These are the three components of the magnetic field. So your field is going from 760 here up to about 830. And you can see it has structure in it. And I don't have time to get into it, but it's associated with those big Alfvén waves that we talked about previously. Okay, so how about how the wind comes out, and how does this have to do with the structure of the magnetic field at the sun? Well, as I showed you, the mapping of the magnetic field from the sun into the corona can be very complicated. And one can try to measure that by asking himself or herself how deformed the magnetic field is as I move from the sun to far away, okay? So if you take like a small circular element at the sun with all the magnetic field lines associated with that, remember magnetic field lines are essentially convected by the wind, and then you go far enough away and you ask what happened to that circle? How did it get deformed? And then you measure essentially the major axis to minor axis dimension at a certain distance from the sun. You call that the squashing factor. And it shows up here, it's measured here in log. And see, here you see the magnetic field. This is a typical solar minimum magnetic field where you have two big coronal holes. But you see that this squashing factor is extremely intermittently distributed. You see how fine scale it is here. And so a conjecture came about saying, well, maybe the complexity of the field leads to additional heating, and paradoxically, this additional heating is going to actually slow down the solar wind, because if you heat the gas in the corona low enough, the corona, you increase how many particles come out, and you have that amount of energy, but if you pull out more particles, the energy per particle is going to go down, and so the wind's going to be slower. So that idea came about, associating this high squashing factor with slower solar wind. There's another component that comes from the heliospheric current sheet, and we know that from SOHO and from stereo that blobs tend to be emitted by the heliospheric current sheet. It's unstable, and that current sheet releases plasma in the form of blobs, and this is a measure of the speed of the blobs as a function of distance from the sun. And incredibly, that's kind of a Parker solar wind model, but it also fits these blobs coming out of the sun, okay? So it wasn't clear from these measurements in stereo whether this was typical and happening all the time, but we'll see in a moment that in fact it is. So finally in 2018 we managed to launch Solar Probe and then Solar Orbiter with the goal of going close enough to the sun to see the origin of the solar wind. And I don't know how I'm doing for time here, but how am I doing for time? Is anybody here to tell me? Oh, okay. All right, anyhow. So we're trying to figure out what happens in this intermediate region, and essentially the same way, you know, what are the details of how the solar wind works, and then how does the magnetic activity, flares, and solar eruptions lead to the hetosphere that we know? And I haven't really talked about energetic particle populations, but their fundamental issue it would deserve a separate talk, is how the cosmic rays coming from the sun are distributed in space and time and how they're associated with solar flares and coronal mass ejections. And of course, Solar Orbiter also moves itself away from the ecliptic, and so wants to figure itself, see the hetosphere from above the ecliptic plane. All right, so this is Solar Probe. Solar Probe has now been in its terminal orbit, which is perihelion at 9.85 solar radii and aphelion at Venus, essentially 0.77 astronomical units. And it has now completed its 28th perihelion, June 8th. And it's spent 35 hours inside 10 solar radii. So that we have now measurements inside the corona below where the solar wind is slower than Alfvén speed, so subalfvénic region of the solar wind, for a fairly long time. And Solar Orbiter is now on its way outside of the ecliptic. And because it has telescopes, we're finally hoping to get a clear view of the magnetic field at the photosphere in the polar regions of the sun. If you remember that diagram that I showed you at the beginning with the rush to the poles, you saw the sunspots coming down, and then you saw the rush to the poles, and you saw there was a latitude separating things that went down from things that went up. And that latitude was about 55 degrees. We can't measure the field properly there. It's very difficult because the Zeeman effect is hard. And so when you go beyond, you can only see the radial component. It's very difficult to see that. But if you move out of the ecliptic and move up to, say, around 30, 35 degrees, then you can measure what's happening. And you can measure the flows there if you have a long enough time. And we need to figure out what happens to the magnetic field, how the dynamo works, what's going on at that latitude, why do things overturn there, and you have the difference between the polar and the sort of equatorial behavior. Okay, so this is the first image of the solar wind, magnetic field, and velocity field seen by Parker Solar Probe. This is the first perihelion, 35 solar radii, halfway from the sun to Mercury. And this is the measurement of the magnetic field, the radial magnetic field in black. Okay, so what do you see? First of all, you see that the nanoteslas are much bigger than what people were used to seeing in space. We're down to 100 nanotesla at perihelion. But then you see that this field is oscillating up and down dramatically all the time. You might think these are crossings of the heliospheric current sheet, but it turns out that they're not. So how can you tell? Well, you can there are many ways in which you can tell. One interesting way is that electrons, fast electrons, always come away from the sun. So if you cross the current sheet and you ask yourself, what is the angle between the flow of electrons and the magnetic field, that would flip by about 180 degrees. Because if the field's coming out and the electrons are coming out, they're parallel. And if the field switches sign at the sun, the electrons are coming out, that becomes 180 degrees. On the other hand, if these fast electrons are coming out and the field is just coming out but bending back, then that angle stays the same. And by looking at that, you can see that all these highly oscillating things are actually folds in the magnetic field. Point one. Look at the magnitude of the field, green. The oscillation of the field is almost 200 nanotesla in BR, but the magnitude of the field is sitting there, 100 nanotesla. That reminds you of something. Remember Belcher and Davis, 1971. Let's look at the velocity field. Velocity field is made up of a baseline, jets coming only up, and they seem to be correlated with these reversals of the magnetic field. These are the other two components of the B and of V. What are these? These are huge, spherically polarized Alphen waves. Humongous. You could think of them as being mavericks in the solar wind, the equivalent of huge ocean waves in the solar wind. The magnetic field, remarkably, is almost constant. So this Alphen wave, suggested by Hans Alphen in 1970, turns out to be the single most obvious and dominant feature of the turbulence and flow in the young solar wind. It's everywhere. 35 solar radii, this thing is everywhere. And I will show you tomorrow in detail what the Alphen wave is and why you have these radial jets going only one direction. Okay? This is a more details showing you how constant the magnetic field is when the magnetic field is moving around. And these are all the perihelia. And as you move in, so this is early perihelia, you can see these radial oscillations faster, and they become a little bit smaller at the closer perihelia. When you see these big switches, these are crossings of the heliospheric current sheet. This one here, this one here. This is kind of a confusogram, but it shows you essentially all of the perihelia of solar probe, up to 23rd. And this is a current sheet crossing. So you see that there's the amplitude of these things kind of goes down as you move closer and closer to the sun. And there's a reason for that that we'll get into. Probe actually manages to measure the local acceleration of the solar wind because it's moving in really fast. And when it's far away from the sun's rotating faster than the probe. But when it's at perihelion, it's going much faster. And so there's a piece in between where it's moving around the sun at the same rate at which the sun is rotating. And so it's just moving in and out, but sitting on the same region of the sun. And so when you go and plot the solar wind, so you have to put longitude in the intrinsic solar frame, and you can recognize the same stream more than once, and you can actually try to measure the acceleration of the solar wind over a certain range of distances. So it gives you data points for your solar wind models that you need to be able to fit. Solar Orbiter has also helped measuring the acceleration of the solar wind in detail because it has conjunctions with Solar Probe and with other spacecraft. And so it gives complementary. And you can see here also these radial jets that correspond to these huge Alfvén waves. And this is an overall plot of the solar wind. This is the first 23 perihelia. This is the latest perihelia. And I've overplotted the radial scintillation measurements. And you see that for most of the early probe orbits, we tended to have fairly slow solar wind. We were in the ecliptic plane, going around the sun, and most of the time, most of the wind was fairly slow. And only recently have we seen faster wind with Parker Solar Probe. There's turbulence. I'm not going to get into the detail, but you see spectra. The turbulence, in fact, is anisotropic. It has different properties parallel to the field and perpendicular to the field. Tomorrow is the time that we'll get into some of the details of that. And this is only a little better. This is showing you the fact that the solar wind has always an intermittent component made up of plasmoids propagating away. Projection is worse, but you can see all these movies on the WSPR website, and you should spend time looking at them because you see things when you look at them okay, so there's a big mass ejection that you see there. Okay. The forming heliospheric current sheet is unstable. We've seen evidence of it in the blobs being emitted. Now we have direct in situ measurements of the jets, the outflow jets from a reconnection X point. We'll discuss this tomorrow more in detail, but we now have measurements, and I think probe has definitely shown that the forming heliospheric current sheet is intrinsically unstable. So the process that leads to the opening up of the magnetic field is not a smooth process. It's a process that opens and closes. It's like a fountain. If you imagine sending a fountain upwards, the tip of that fountain is always unstable. It's never stationary. You can take an average, make it look stationary, but it's always jumping up and down. It's always unstable. Distribution functions. Close to the heliospheric current sheet, we see distribution functions that look like this. This is the radial component, this is perpendicular, and so you see what have been called hammerhead distribution functions. So we see distribution functions that are quite different from the smooth bicycle seat that we saw much further out. We still see things happening in the direction orthogonal to the magnetic field, but in a much more detailed and complex way. Okay, so that's kind of giving you a panorama of what we've seen. Now, what happens when you go far enough away? How does the heliosphere end? That's a heliosphere in my sink. How many of you understand that is why that is? Why does this work? Why is this a good heliosphere? Why is this a fairly good analogy with a heliosphere? Well, these are waves in shallow water, okay? So the fountain jet, the jet from your nozzle, you can play with it in your bathtub tonight or in your sink tonight. You should do it. If you have never played with this, it's like a fascinating game. You don't have to wait till you have a 2-year-old to do it. That's a good excuse, but you don't need that. You can play on your own. The jet, in shallow water, the waves are very slow because they go like the depth. And so that's very shallow. So the waves are slow. The flow is very fast. Okay? So this is supersonic. From the point of view of water, that flow is supersonic. But then what happens? Typically, the sink has a little bit of curvature, but even if it doesn't, that water has to accumulate somewhere. At some point, the water becomes thick enough that the flow becomes subsonic, and you form a shock wave. That's the shock. But the shock, we like to think of shocks as being steady and stationary, but that water example teaches you the shock is never really stationary. It's always a mess. And this isn't a flow. This is a fluid flow. In a plasma, where things depend on whether you're along the field or perpendicular to the field, you can imagine what that's going to be like. It's only by taking huge averages that things are going to look stationary. But if not, they're not. And of course, this is a bad heliosphere because it supposes that the sun is not moving in the interstellar medium. A better analogy is this sink. How did I go from this sink to this sink? Somebody tell me, how do I go from this to this? What did I do? Yeah. Yeah, exactly. Thank you. It's very trivial, right? So I took that little pan that I had put under there, not to show the hole of my dirty sink, and inclined it a little bit. And so now it's as though gravity is playing the role of acceleration. And so essentially, I now have a bow shock, a beautiful bow shock forming, right? So now we want to do that. We have to decide where we are. So this is our galaxy. That's where we are. This is the local interstellar cloud, and this is where the sun's moving. And this is the termination shock. This is the heliopause. And there's as I said, there is no outer shock. And the reason there's no outer shock is that there's mass loading from the interstellar medium towards the sun. So the mass is continuously going up, and that smooths the transition that would otherwise be a shock because the sun is actually moving supersonically, 100 kilometers per second in the interstellar medium. And there are 2 missions, IBEX and now IMAP, devoted to trying to understand the topology of the magnetic field and the distribution of matter in the local interstellar medium and teaching us what the overall shape of the heliosphere is. And, whoops. So there we go. So the local interstellar medium parameters, the local interstellar medium flow may be either marginally super fast magnetosoccer or subfast. There's a lot of neutral hydrogen, and therefore we don't probably have a bow shock, and I think Voyager has now shown that. One of the interesting things was that the energetic neutral atoms shown by IBEX to have what's called the IBEX ribbon, you probably all have heard of. And that ribbon is thought via very simple models, simplistic models, to essentially identify the way in which the magnetic field wraps around the heliosphere. So we have now models of the overall shape of the heliosphere. So inside here there's the sun with a termination shock, and then the flow is deflected around the sun as the sun moves into the interstellar medium, and the ribbon essentially displays the angle with which the magnetic field comes around the heliosphere itself. And these are simulations that was done by Merav. I'm sure there are better ones now, probably 6 years have gone by. But this is a kind of an idea of the shape. So the other fascinating thing, of course, that you see here is that, and it's also a characteristic of the plasma that we'll define better tomorrow, is that similar processes occur on widely different scales. So we have little loops on the sun that might produce microscopic current sheets. Then we have big loops on the sun that produce the heliospheric current sheet. And then we have humongous shapes in the interstellar medium, but it's always magnetic fields interacting with charged particles on different scales. And there's a whole regime, there's a whole region of scales where the scales don't count. And that's the that's why people are so much in love with magnetohydrodynamics. Magnetohydrodynamics does not contain scales. So if I invent a theory of magnetohydrodynamic turbulence, it can apply to the solar wind exactly in the same way it can apply into the accretion disk of a black hole, because essentially it's scale-free, as long as I don't touch the dissipation scale and the injection scale. But we'll discuss that more tomorrow. So I think I'm finished here. Right, and so that's tomorrow. Thank you. Yeah, questions or more, if you, or criticisms, that's fine too, you know, whatever. Bye. So then we'll. Sure. Well, the cue, the squashing. Why is it this? Right. This is. Well, maybe it's myself. I probably turned it off by mistake. It's okay. It's okay. All the way back. Oh. Here we go. Yes. Please.
I noticed there's kind of self-similarity in these arches that kind of go. And I've seen pictures like that in nonlinear dynamics when you look at attractors.
Yeah.
They have a very similar structure. Is this a coincidence, or is there like
No. I don't think it is. So, the friend has let me try to reformulate your comment. So he's saying, when I look at that, it reminds me of strange things that I see in self-similar sets in mathematics, like attractors, or when I plot the dynamics of a nonlinear, slightly nonlinear system, where I see the orbits accumulating in a certain region, then jumping over into a different place, etc. Well, it turns out that there's a formal analogy between the evolution of a magnetic field with distance and the orbits of a particle in a nonlinear system. There is an analogy. And the distribution of the magnetic field on the sun is, to some extent, self-similar over many, many scales. And so the number of, let's call it critical points or singular points of the field as a function of height decreases. And so I think you're correct. There is an analogy. How far that has, it's beginning to be explored more today than it has been in the past, but it's essentially virgin territory for many things.
Can you go to the switchback plots?
Which ones? The ones at the end?
Yeah,
That one?
maybe the last one, or the one before. Yeah.
This one?
Yeah. So,
That's only the magnetic field, yeah.
so based on, say, the direction of the radial component of the magnetic field,
Yes.
is it possible to distinguish whether the switchbacks are due to the processes happening in the solar corona or due to turbulence in the solar wind?
That's a good question. I'll try to address it now in part and then in part tomorrow. So we haven't discussed the structure of an Alfvén wave, okay? So I need to say a few words about that to be able to answer your question. So in an Alfvén wave, as proposed by Alfvén, what happens? The magnetic field in the fluid picture has tension in it. So when you deform the magnetic field, like an elastic band, it bounces back. And just like in exactly analogy to the violin chord or an elastic band, you have a magnetic field perturbation and a velocity perturbation that are perfectly correlated. And they propagate along the mean field, okay? So let's imagine now that we have a mean field going from me to you, for simplicity. In the wave that propagates from me towards you, magnetic field perturbations and velocity field are anti-correlated. So delta V is equal to minus delta B. If the field is coming from you to me, the wave that comes, I'm the sun for this instance, I'm not the sun by all means, but the correlation changes. So delta V becomes plus delta B, okay? Now, the only thing I can really say when I look at these is that the correlation is such that these are always coming from the sun. I never see something that in the frame of the solar wind is moving towards the sun. It's always coming away from the sun. Therefore, intuition tells us that the waves must originate at the sun. Otherwise, why would there be a predominance of waves coming? I'm in the frame of the plasma, okay? Remember, most of the time we're in the supersonic, superhelvenic wind, so both waves propagate outwards because they're advected by the solar wind so fast that I would see both. They both are advected outwards. If you're in a supersonic medium, both sound waves come forward, right? So how do I tell where these originate? Okay, so they're clearly coming from below. How do I tell where they're coming from the sun or they're generated between the sun and me? Well, we have to make theory or models, and we need measurements. What kind of measurements might tell me whether this structure is born, say, in the lower corona? Well, perhaps if reconnection is involved, then there might be some compositional differences, some ratio of minor ions that has some property. So I might look for composition differences. On the other hand, if it's generated in situ or by just standard turbulence mechanisms that we'd have to get into, I wouldn't expect to see a composition difference. Maybe that's one way in which you can tell. If you ask my intuition, what my intuition, I think that the main process which leads to these is the fact that these are waves that are propagating in an expanding medium. And so there's a little bit of magic involved, and we'll get into it tomorrow. But what happens is that because the medium is, the density is falling down, the relative amplitude of the fluctuation grows, and at some point, it's become so big that it reverses the field. That does not mean to say that some of those, the origin of those waves might be in reconnection in the lower corona, or it might be from below, from coupling of waves in the chromosphere. I can't distinguish between those two directly unless I measure. And if I think, since I strongly believe that nature is not normative, so nature is not German, it's more Italian. What do I mean by that? In Germany, or in the German system, anything that is not expressly legal is illegal. In Italy, it's the only nation in the world where there are two different kinds of illegal. If you go to a train station in Italy, you'll see that there's è vietato, which means it's illegal, and then it's è severamente vietato. It's really illegal. It's strongly illegal. It's the only country in the world that has these two different things, descriptions in Italian. Because in Italy, anything that's not expressly illegal is legal. In fact, oftentimes it extends a little bit further. So nature is like that. Anything that does not violate a fundamental law, even if it might seem improbable to you, I think happens somewhere in the universe, for sure. And both of these possibilities are not illegal. So if I think that once we do get measurements of compositions, we'll find switchbacks that are born and have compositional differences, and I'm willing to bet that we'll find switchbacks that have no composition signature. They're going to both be present. And they will tell us that some of these switchbacks don't come from reconnections, but others do. That's my intuition.
I have a question about this same thing. You have just talked about this Alvin waves, right? They're constantly coming out of the sun, right?
Yes.
In radial distance.
Yeah.
So my question is, like, if they are coming in outside always, then how, like, they will be in the same speed. Like Alvin velocity, if you calculate at a particular position, you have velocity, you have magnetic field intensities, and you have density. They are all coming in the same direction. So there is no point of interactions.
There's no?
There is no point of interaction between them, right?
Yeah.
The Alvin waves.
Yeah, sure.
So then, how can it be turbulent? So turbulence means, suppose, some wave interactions. So if they are like coming to the same direction, then how
That
will they
is a
interact?
very good question. Now, let me say something that we'll get into in detail tomorrow. Let me say something. Switchbacks are driving me crazy, okay? Because they're deceptively simple. But when simplicity becomes so simple that it's deceptive, you hit something, there's something horribly wrong in the way I understand some very basic things. So let me explain. So you see all these jets coming up, right? Sometimes people think these are jets. And so since you see a jet here that's higher speed than one next to it, they say, well, it's going to catch up with the other one. But it's not. Because this jet is part of the spherically polarized Alfvén wave. So what's really happening is that, so this is the perversion of the nonlinear Alfvén wave. Okay, so what's happening, really? The magnetic field line is doing this, okay? The wave, the perturbation, so to speak, only knows the world in its local place where it is. So when the magnetic field goes down, that thing would like to propagate, since the field's going back, it would like to propagate backwards. But it can't, because it's part of a guy that's going that way. So as this thing happens, the Alfvén speed goes down, but the velocity field goes up. That's why you see the jet, in such a way that the sum of the two, which is the actual speed of the object, stays the same. That's this weird, large amplitude Alfvén with it that I'll show you via equations. I'm not telling a fantasy story here. That's what MHD does. This thing exists. It's a nonlinear wave. It's an exact solution of the MHD equations that does this. But it has some implications for the transport of energy and momentum, which are non-trivial. That's the reason. The jets are only apparent. Now, why is there a spectrum? You could imagine that the spectrum is born out of the way these things are generated. It could be simply an advected spectrum, for all you know. It's not, because we have evidence that the spectrum is evolving with distance. So there are nonlinear interactions. Nothing is perfect in nature, right? So when I say the field is constant, yeah, it's quasi-constant, but it's not constant. In fact, you can prove that a locally generated switchback cannot have constant magnitude magnetic field everywhere. It has to have, because of magnetic flux conservation. If you can imagine, so imagine you have an unperturbed field way at the door and here, okay? So if there's a switchback in between, the field has to come back up, goes up, come back down, and go back up, all right? But in that region where it comes back up, comes back down, and count the number of field lines. Now you have more field lines crossing that, i.e., there's a bigger magnitude of the field. You cannot keep the magnitude the same. So somewhere, if you want to localize it, you have to change the magnitude of the field. You cannot, so it has to kind of, in other words, the only way you can do this, keeping the magnitude constant, is you have to expand it as you go. This structure has to expand. So it's a little bit more complicated. So you can have nonlinear, so spherical, it's tomorrow. It's too complicated now. But there's more things that I don't understand than I do, so.
I have two questions. So,
Pick one.
oh, okay. So can you comment on the difference between non-alphenic slow wind and highly alphenic slow wind and their source regions?
Yes.
And maybe on like
oh,
the
you're touching
diagnostics.
you're touching a topic which is of extreme interest. Okay, there are some regions where alpha waves can't propagate. What are those regions? Regions where there's no magnetic field, or regions where a field line goes up and comes back down. Why? Because then on one side the alpha waves come this way, on the other side the alpha waves come this way. They cross each other, they interact, and they destroy each other. Right? So the heliospheric current sheet, in the current sheet, you don't expect to see alphenic wind, for sure. Then, imagine that we have a source of alpha waves at the sun. This idealized thing about alpha that I was talking about is true in a homogeneous medium. But we saw that the medium is not homogeneous. So in particular, just like in optics, the alpha wave, geometric optics is not good for alpha waves, but for this particular illustration, it is. If you have a speed which changes, then you corrugate a wavefront, right? Because the wavefront's going to move faster where the speed is faster, it's going to move less where the speed is slower. So for example, imagine now you have a region with large magnetic field, low density, and then you have a region with large density and low magnetic field. And below, some perturbation happens. Well, here it's going to go fast, here it's going to go slow, and the wavefront is going to become corrugated. And sooner or later, that corrugation is going to become significantly small scale that you're going to start dissipating the wave via some mechanism, interactions with particles, whatever, when you get to small enough scale. So you're going to start destroying these outwardly propagating waves where you have very strong gradients. Now, coming back to what our friend said about statistical mechanics, oh, sorry, I was going the wrong way. So those regions with high squashing factor are regions where the mapping of the field is almost singular. So two field lines that start out close together can diverge. Those are regions where any wave is going to have a hard time propagating across because it's going to dissipate because of the divergence of the field lines. So if you ask me, I would argue that non-alphenic wind has to do with regions that are complex from the point of view of the magnetic field geometry or the heliospheric current sheet. While the rest, where the field is okay, you know, the mapping's not too complicated, they're going to be alphenic. At the sun, the alpha waves want to be born everywhere, I think. That's what Parker shows. Yes. And then, if you don't see them, it's because they get destroyed on the way.
Go to David.
Actually, it's not about waves. So it's exactly about this figure. So
Okay.
it's probably written in the paper, but what exactly causes this sort of croissant shape and not something like magnetosphere, similar thing with continuation of this current sheet on another side of magnetic field?
Well, that's okay. That's interesting. I think I can give you an answer to that. Okay, so what happens to the magnetic field of the sun, right? So in the North Pole, remember the ballerina skirt. So on one side it's wrapping like this.
Orient this, where's the North Pole on this thing?
Like this. Okay. So imagine the axis to be like this, right? So here you have this cone of rotating field this way, and underneath you have a cone rotating the other way, and then you cross the shock, it becomes more intense, and then you have the draping from the outside field. So what happens, it's kind of funny. So what happens is that after the termination shock, the flow from the solar wind has to get deflected back around, and then it has to encounter the field coming from outside. Now the magnitude fields is comparable. And so what happens is that this deflected flow carries these cones of flux around. It's like a slinky. Somebody squeezed it in the middle and then pushes it around. And that doesn't give you, it gives you more.
What it
something like
reminds
that.
me of maybe induced magnetosphere of Mars. So it
Yeah,
still
probably.
has some sort of magnetotail.
It does.
And here we
These-
sort of see two lobes separated from each other without current sheet between them.
Oh, because the field is just so weak. It's not, here the field is tangled. If you plotted the current here, you would see currents, very singular currents. It's as if the current sheet's not quasi-laminar, but there are current sheets in that system. It's not very strong, but it's not, in other words, the field from the sun is more important here than the field from the outside in reality. That's the way I see it, at least. I may be wrong. I mean, Nick might know the answer to his question.
Yeah, but I'll speculate on a side conversation.
Okay.
Okay, Marco will be here all week, and as Yuri is
Yeah.
scheduled to be here tomorrow morning talking,
Sure.
Following up. So this was a good level setting sort of talk on solar physics and what we know about the sun and solar wind this afternoon.